In the first lecture on Ising model, we have simply defined the Ising model. After some introductory facts, you have seen how Ising model is defined. And we have also seen that basically this Ising model is aimed to discuss the second order phase transition, particularly the magnetic phase transition, when a ferromagnetic material or system changes into a paramagnetic material or system at critical temperature, which is also called Curie's temperature. And we have obtained the energy of interaction in accordance with the Ising model. Now, after that introductory lecture, uh, in this lecture, our aim is to discuss a very important concept which is called Bragg-Williams approximation. Or you can also say that we are going to discuss Ising model in zeroth approximation. Actually, there will be a very complicated mathematics when we will not use the approximation method. So there are several approximation methods to deal with the problem related to the Ising model, and one of them is most important, and that is Bragg-Williams approximation. Actually, by the use of Bragg-Williams approximation, we basically find the several thermodynamical functions of the system like internal energy, heat capacity, entropy, Helmholtz free energy, and so on. So you can say that the basic aim of Bragg-Williams approximation is to find the thermodynamic functions of the system. Okay. In this lecture, as there are several thermodynamic functions which will be calculated by using this Bragg-Williams, not William but Williams approximation. So for your convenience, I have divided this long lecture into two parts so that you will feel each. So actually in this first part of the lecture on Bragg-Williams approximation, we will only calculate the energy of interaction, and in second part we will be then able to find all other important thermodynamic functions by the use of this very important approximation. Okay. Now, what is this Bragg-Williams approximation, and actually what are the basic assumptions which will be made in this approximation? We will see first of all. In fact, when you talk about the Ising model in this context, Bragg-Williams approximation assumes that lattice is divided into two sub-lattices. Okay, and in these two sub-lattices, one is for up spin and the other is for down spin. That is, one is for +1 spin state and another is for -1 spin state. Okay. Although these sub-lattices interact one another, but in this approximation we simply consider that the sub-lattices are non-interacting, although this is not a real fact. Real fact is what? The real fact is the sub-lattices interact one another, but in this simplified version of discussion provided by Bragg-Williams, actually we assume that the sub-lattices do not interact one another. When you consider that the interacting sub-lattices do not interact one another, then the calculation becomes very easy. So this is called approximate method. Okay. So considering that the sub-lattices do not interact one another, we will be able to calculate the thermodynamic functions or properties like internal energy, as I have told you, heat capacity, entropy, Helmholtz free energy, and so on very easily. Okay. So now let us start how we can find these thermodynamic functions by the use of Ising model applying the Bragg-Williams approximation. And for this, you have to remember what you have learned in the first lecture on this Ising model, which I have provided earlier. You have obtained the expression for the energy of interaction of the system, and you have learned in the previous lecture that the energy of interaction, which is spin dependent, that is given by this expression. This is EI of SI equal to minus epsilon summation over Ij SI times Sj minus mu H times summation over I Si. The different quantities used in this expression are already known to you because you have learned all these things in your previous lecture. Here actually this Si and Sj, these are actually the spin variables. Okay. And when you consider this Ij inside an angular bracket, then you know that this symbol actually refers that we consider the nearest neighbor always in pair of spins. So this angular bracket has been used here. Okay. And when you talk about the isotropic interaction, that is interaction between two sublattices is same everywhere, then this term epsilon is used instead of epsilon ij, and this epsilon ij was actually the interaction energy, but in case of isotropic interaction, this epsilon ij has same value for any value of I and j. So this has been taken outside of the sign of summation. Okay. This mu is actually the magnetic moment per atom or per sublattice, you can say. H is the magnetic field strength. Okay. Now actually we consider in Ising model that the system is just an array of n fixed points which are called lattice sites, and that actually form an n-dimensional periodic lattice where n is simply 1, 2 and 3. And that associated with each lattice site there is a spin variable which is denoted by the symbol Si, where I runs from 1 to n. Okay. And which is a number, and that is actually equal to either plus 1 or minus 1. When Si is plus 1, that represents the up spin, and Si equal to minus 1 represents the down spin. Actually, Bragg and Williams assume that the distribution of spins is at random. Okay. And on a given site, if n plus represents the number of spins for which Si is equal to plus 1. Okay. That is the number of sites where there will be up spin, that number is equal to n plus. And similarly, this n minus represents the number of spins for which Si is equal to minus 1. In other words, you can say that this n minus 1 represents the number of down spins, and n plus represents the number of up spins. Okay. Now, if we consider that the total number of spins is n, then n will be simply equal to n plus n minus. Okay. Now we will actually define the probability of finding of up spin and the probability of finding of down spin, because this spin distribution is random. So, in accordance with the definition of probability, you can easily say that when we will divide the number of up spin, that is n plus, by the total number of spins, then we will get simply the probability of finding a up spin, okay, that is a spin with value plus 1. And similarly, the probability of finding of a spin down will be equal to what? That will be equal to n minus over n, because n minus, you know, is the number of down spin, and so the number of down spin divided by the total number of spin, that will be the measure of probability of down spin, okay. Now, in terms of these probabilities, when we will want to find the expression for the energy of interaction, which I have denoted by the symbol EI, and we have defined it in this equation 1 in accordance with the Ising model. What will be the expression for EI in terms of these probability of up spin and down spin? You can see, actually, you know that the value of this summation over ij, okay, sij, this, as you know, that actually this pair of spins represents a number which is equal to gamma n divided by 2, okay. So this will be gamma n divided by 2. This is actually the this is for this summation sign, and summation over ij sij, this will be equal to gamma n divided by 2, and for sij we will write n plus divided by n minus n minus divided by n whole square, okay. And this factor is present here, epsilon, so we will multiply it by this epsilon, okay. So epsilon times this much is equal to this, okay. And similarly, summation over I si, this will be simply equal to the n plus minus n minus, okay, because we consider the value of n plus as plus 1 and n minus as minus 1. So this summation will be the algebraic sum, and that will be equal to n plus minus n minus. So after substituting these values in equation 1, the expression for this energy of interaction will become like this. You can see EI will be equal to minus gamma n divided by 2 times epsilon, and you know that n plus divided by n minus n minus divided by n square. What will be this? You can simplify it by the formula of a minus b whole square. So this will be equal to n plus by n square plus n minus by n square minus 2n plus times n minus divided by n square, and mu h summation over si, but at the place of summation over si we will write n plus minus n minus, okay. Actually, in this last term I have written n plus minus n minus. It means we are assuming that the value of n plus is greater than n minus. Although it is also possible that n minus is greater than n plus, but our assumption is what? Our assumption is the probability of finding the lattice site in up spin state is greater than that of the down spin state. So we have assumed that n plus is greater than n minus, okay. Now this probability n plus by n does not require any correlation between the nearest neighbors, and it is a measure of long range order. It means this n plus by n, the value of n plus by n is not limited only to the nearest neighbor. It is a long order term, and so for the entire space of the lattice, the value of n plus n will be almost same. And so this is called long range order. Okay. Actually, you will see later on that this n plus by n is related to a parameter which is called long range parameter, and I will denote it by the symbol small m. You will see later on. And in terms of this long range order parameter, we will calculate the different thermodynamic functions. Okay. Actually, this simply implies that in the entire lattice, a fraction of n plus by n of all the spins are up. Okay. And hence, if n plus by n is known in the neighborhood of a given spin, then the same average value is likely to occur everywhere on the entire lattice, as I have told you earlier. Okay. Now, first of all, we will find the value of this interaction energy, and as I have told you, we will find it in terms of the long range order parameter, which is denoted by the symbol m. But what is this long range order parameter, and what will be the expression for it? For getting this idea, first of all, we will find the total magnetic moment associated with the spin of the lattice sides. As you know that mu here represents the magnetic moment per lattice point, So, if you talk about the total magnetic moment, then you know there are n plus up spin lattice point and n minus down lattice point. And the value of a spin for up spin is +1, and that of for down spin is -1. So the total magnetic moment will be the algebraic sum of the magnetic moments of the different lattice sides. So the total magnetic moment for up spin, that will be mu n plus. Okay. For up spin, total magnetic moment will be mu times n plus, because you know mu represents the magnetic moment per lattice point. Okay. And the total magnetic moment for the down spin, this will be mu n minus. But the value of mu n plus, you know, is positive, and value of mu n minus will be negative, because we are talking about up spin whose value is +1 and down spin whose value is -1. So we simply add these two values algebraically. Okay. So this mu n minus 1 will be actually negative. And so in other words, we can also say that if a magnetic moment, let us say m1, or you can say m plus, is directed up, and a magnetic moment m minus is directed down, okay, then what will be the net magnetic moment? As we have considered that n plus is greater than n minus 1, so the value of this m plus will be greater than m minus, and so the resultant magnetic moment will be m plus minus m minus. Okay, but m plus, you know, this will be mu times n plus, and m minus will be mu times n minus, and so this will be mu times n plus minus n minus. Okay, so I have written here, you can see that the total magnetic moment m will be equal to mu times n plus minus n minus. Okay, now we will replace this n minus from this equation in terms of n, and for this, you know, the total number of lattice point n is equal to n plus n minus, And so from here you can see that n minus will be equal to this much. This is n minus n plus. So replacing this n minus from equation 3 by this expression, you will get m is equal to mu times n plus minus this much. So this will be minus n and plus n plus. Okay. Now n plus n plus, this will be 2n plus minus n. So m is equal to what? This is mu times 2n plus minus n. Okay. Now we take this n as a common factor. So you can write this expression as mu n times 2n plus divided by n minus 1. Now let us divide by this factor mu n to this m, and so your result will be m divided by mu times n, and that will be equal to 2n plus 1 divided by n minus 1. Actually, this quantity 2n plus 1 divided by n minus 1, this is just a number. This is represented by the symbol m, and this m is actually called the long range order parameter. This is called long range order parameter. And as I have told you that this all the properties will be calculated in this long range order parameter, and you will see that the value of this m lies between minus 1 and plus 1. So you can say this minus 1 is less or equal to m, and this is less or equal to 1. Okay. This is its range, long range parameter. Okay. So you can say from this result that this 2n plus divided by n is equal to 1 plus m by mu n. Okay. And so n plus divided by n will be equal to 1 over 2 times 1 plus m by mu n. Okay. And as you have seen that this m divided by mu n, this is equal to m. So instead of this m by mu n, you can write m, and so the expression for n plus divided by n becomes 1 by 2, 1 plus m. Okay. Now, as we have calculated the value of the probability of up spin, which is n plus by n, and its value is 1 by 2 times 1 plus m, where m is called long range order parameter. Similarly, you can make a calculation to get the value of n minus divided by n. You can easily see. And if you want to calculate this the value of n minus over n in the similar way, you have to replace n plus from this equation 3. For getting the value of n plus by n, we have replaced or eliminated this n minus from here. And in the similar manner, we can replace this n plus from this equation 3. And for that, you can see this n plus will be simply equal to what? N plus will be equal to n minus n minus. Okay. And when this will be replaced, then your result will be actually what? N minus 2n minus. So at the place of 2n plus, there will be 2n minus 2n minus. So the expression you can write for n minus by n directly by induction on the basis of this equation 3. I have not actually made the calculation. You can do it if you want to do so, but you can remember or you can write the expression for this n minus by n just observing the value of n plus divided by n defined in equation 5, and that will be simply equal to 1 over 2 1 minus m. What will be the result? That will be 1 minus m. So you can see I have directly mentioned here that n minus by n will be equal to 1 over 2 times 1 minus m. Okay. Now, in terms of this long range order parameter m, you have calculated the value of n minus divided by n. You have also calculated the value of n plus by n as in equation 5. Okay. So this term n plus by n, n minus by n, both have been calculated in terms of the long range order parameter small m. And now our aim is to find what will be the value of this n plus minus n minus in terms of the long range order parameter m. And then we will substitute all those values in this equation 2. Okay, to get the expression for interaction energy in terms of the long range parameter small m. And for that you can see that the another term was 2n plus times n minus divided by n square, and this can be written as 2 times n plus by n minus times n plus by n minus. Sorry, this is actually written wrongly here. You can see this will be not plus, this will be not minus, not minus. Actually this will be n minus. So this is 2 times n plus by n times n minus by n. But n plus by n, you have just calculated that this is 1 over 2, 1 plus m. And n minus by n, you have calculated in this equation 6 that this is 1 over 2 times 1 minus m. And as here there is a factor 2, so one of the 2 will cancel out and your result will be 1 over 2 times 1 plus m times 1 minus m. Okay. Now, as I have told you that our aim is now to find what will be the value of n plus minus n minus, because in last term of equation 2 this term exists. So you can see this equation 3, equation number 3, and from this equation 3 we can say that this n plus by n plus minus n minus, this will be simply m divided by mu. So I have written here, you can see that m by mu is equal to n plus minus n minus. Okay. And if we will divide both sides of this equation by n, our result will be what? Our result will be m over mu n equal to n plus by n minus n minus by n. Okay. But you have seen earlier that this m divided by mu n, this is represented by the symbol m, which is called long range order parameter, and this m will be then equal to what? This will be 1 over n times n plus minus n minus. And so you can write this n plus minus n minus is equal to mn. So in this way you can see from equation 4, starting from equation 5 to 8, we have calculated all the terms appearing in this equation 2, which represents the energy of interaction. So you have found the value of n plus by n in terms of small m. You have also calculated n minus by n in terms of small m. You have then find the value of this 2n plus 1 times n minus over n square in terms of m. And finally we have calculated the value of n plus minus n in terms of small m. So now we will substitute all those values in this equation 2, and then the expression for energy of interaction, or you can also say internal energy, we will get in terms of the long range order parameter small m. So now let us substitute all these values in that equation. So after substituting the value, you will get EI equal to minus gamma n over 2 times epsilon. You know gamma is coordination number, okay? And this will be what? The first term is n plus divided by n square. But you have obtained that n plus by n, this is equal to 1 by 2 times 1 plus m. So after squaring, this will be 1 by 4, 1 plus m whole square. The second term was what? The second term was n minus by n, and that was equal to 1 by 2 times 1 minus m. So after squaring, this will be 1 by 4 times 1 minus m whole square. And the third term was 2 n plus times n minus divided by n square. And you have obtained the value of this 2, and you have seen the value of this in terms of the long range order parameter small m is equal to this much. This is 1 by 2 times 1 plus m times 1 minus m. Okay, and the last term is minus mu h times n plus minus n minus. But you have seen just now that this n plus minus n naught is equal to mn. So I have substituted here mn at the place of n plus minus n. Okay. Now we will simplify the RHS of this equation a little bit. The factor outside of this square bracket remains at each, you can see. And now we will expand 1 plus m whole square and 1 minus m whole square. And we will take this 1 by 4 as a common factor. So this will be what? This will be 1 plus m square plus 2m, okay, plus 1 plus m square minus 2m. So this 2m and 2m will cancel out. Now 1 plus 1 will be 2, and m square plus m square will be 2m square. So we will take 2 as a common factor, and that 2 will cancel out, and here there will be a number 1 by 2, and the remaining factor will be 1 plus m square. Now again this 1 plus m times 1 minus m, you know this is 1 minus m square. Okay. So inside this square bracket, now the terms are 1 by 2 times 1 plus m square minus 1 by 2 1 minus m square. Okay. And minus mu h mn. Okay. Now here when we will simplify it, our result will be simply equal to m square. This minus this will be equal to m square. Now let us multiply by this outside factor, and your expression for interaction energy or internal energy EI will be what? This is minus half gamma n epsilon m square, okay, and minus mu h mn. This is actually the expression for the internal energy of the system, or for the interaction energy of the system, on the basis of Ising model applying the Williams-Bragg approximation in terms of the parameter m, which is actually called long range order parameter, you know. And as I have told you that the value of this long range parameter m lies between minus 1 and plus 1. Okay. Actually this long range parameter m, you will see later on that this actually represents the magnetization of the ferromagnetic system, and it also represents the dielectric polarization on a ferromagnetic system, and so many other magnetic properties. And as I have told you in the beginning of this lecture, that in this lecture we will only calculate the interaction energy or the internal energy, and rest of the thermodynamic functions will be calculated in the second part of this video, because then you will feel actually convenient. Okay, so I think you have definitely understand each and every step of this video clearly, and so I will suggest you watch the video seriously with your pen and paper, write down in your notebook, and again revise it. Everything will be crystal clear. Okay, thank you very much.